Okay, let's take a look at some circuit reductions. In this case, we're going to look at solving parallel resistor circuits using an analysis in circuit reductions by simplifying the solutions for the special cases. So you'll recall that the general expression for resistors in parallel, the total resistance is equal to 1 over the reciprocals, which ends up being the conductances, but 1 over R1, the sum 1 over R2, 1 over R3 out to the nth position or the end of the ladder. So let's take a look here. First example here, the general expression for finding the total resistance for any number of resistance in the parallel is given by the general expression. From this expression, though, we can derive one of the special cases of a total resistance where we only have two resistors beginning with the general expression. So in looking at this, we're going to limit ourselves to just R1 and R2. So we can simplify the general expression by getting rid of the rest of the terms in the denominator, and we end up with the total resistance then is equal to 1 over the reciprocal 1 over R1 plus 1 over R2. So the thing that we have to do now is use what we learned in creating common denominators, because we cannot simply sum R1 and R2. So we create a common denominator with R1 and R2. And that common denominator then becomes the product of R1 and R2, which would in effect be the factors. Okay, so R1 and R2 would be common to both of the expressions, and all we do is cross multiply. So the first term becomes R2 over R1 by R2 and R1 over R1 by R2. So that's sum. So now we can sum those values. So when we sum those values, we end up with R2 plus R1 over R1, R2. So in the next step then, since we have a relationship then where we have a common denominator, we can combine our terms. So R1 plus R2 in the denominator divided by R1 over R2. Since it's all over 1, we can simply do an inversion here. We can flip over the denominator and put it in the numerator, and we end up with the product, R1 over R2, over the sum, R1 plus R2. So in electronics, we like to call this the product over the sum, and this relationship is a relationship that we will see going forward in our studies and will be handy in other applications like the current divider rule. So let's look at another special case. Again, we will start with the general expression. A special case of parallel circuits in the parallel connection where we have resistors of the same value. So from the general expression, we will derive the formula for several resistors in parallel having the same resistance. So we're going to limit ourselves to, again, just two resistors, R1 and R2. But in this case, R1 and R2 are the same value, so we can just call them R. Well, that makes it a lot easier when we have to do our common denominator, because what we end up with then is then 1 over R1 plus 1 over R1, which simply becomes 1 over 2 over R. Again, we just invert the denominator into the numerator, and we come up with a total resistance of R divided by 2, or half the value of R. And this will become valuable to us again when we do more parallel circuit analyses and simplifications, because we can tell by inspection that we're going to have values of resistances where we have like values that become smaller than the smallest. So we end up with, again, a simplified expression in this case of R divided by 2. In the last one, what we want to do is take a look at what we determined from early on, where we can use one to solve for the other. So in this case, we're going to identify R1 and R2 as X and A. X will become some unknown we're solving for, where we know some value of the resistance A. So sometimes you need to determine the values of resistors that are to be combined to produce a desired total resistance, If you know, or if you want to arbitrarily choose one resistor as R sub A, then you could calculate for the unknown second resistor value R sub X by using the, again, general expression, which we simplify to two resistors. So we're going to take what we originally had for our general expression, simplify it down to two resistors, R1 and R2, and in this case we're going to call R1A and we're going to call R2X. So our relationship then becomes, where we solve for 1 over the total resistance, simplifies to 1 over R sub A plus 1 over R sub X. Okay, so all we did was invert and pull the denominator, the value out of the denominator. What we did to one side, we had to do to the other. So this sets us up for a simple combination of terms here and allows us to solve for the unknown. So what we're going to do is we're going to isolate the unknown, R sub X, to the left side of the expression, and we're going to isolate the factors on the right side of the expression. So 1 over the total resistance now minus 1 over the known value R sub A. So we're going to do a cross multiplication here so that we can get a common denominator. So multiply the first factor by RA, top and bottom, multiply the second factor by R sub T, top and bottom, and we end up with RA minus R total divided by the product RA over R total. So one more flip. We're going to flip the unknown R sub X into the numerator. We do the same thing on the other side with the factors, and we end up therefore with R sub X, our unknown, is equal to the product R sub A over RT over the difference in this case, because we moved one term to the other that created the difference. So it's kind of like the product over the sum, but now our sum is a negative value. So we end up with a simplified expression here that we can use to solve for an unknown resistance, given that we knew the total resistance and the value of the first resistor, R sub A.